Hello and welcome to this session in which we will consider the analysis of a turbine and see how we can find out the various states and how to address the performance of a turbine. So, we are given that we have a small turbine which delivers 150 kilowatt of power. So, let me first draw the turbine. So, the power output, the work done by the system is 150 kilowatt, this is W dot turbine. It is supplied with steam at 700 degrees Celsius and 2 megapascal. The exhaust passes through a heat exchanger where the pressure is 10 kilopascal. And it exits as a saturated liquid. Okay, this is the information that we have. So, the thing about heat exchangers is ideally the pressure drop is quite negligible. As a result, the inlet and the exit of the heat exchanger are both held at 10 kilopascal. So, it is given that the turbine is reversible and adiabatic. Find the specific turbine work and the heat transfer in the heat exchanger. So, the specific turbine work is equal to this divided by the mass flux, okay. And the heat transfer in the heat exchanger is simply found out by writing down the first law for this particular control volume. CVHX is the control volume of the heat exchanger. So, we have Q dot plus M dot HI total plus M dot minus M dot HE total minus W dot is equal to 0 at steady state, steady flow process. Okay. And so, because in a heat exchanger there is no work done, we have Q dot Hx is equal to M dot He minus Hi. And if a turbine is reversible and adiabatic, what does it imply? It implies, as you might have done in the theory class, that the turbine is also isentropic. So, if it is isentropic, the entropy at this point, so let me call this as S1, if I call this as S2, S1 is equal to S2. So, let me quickly write down the values. I have T1 is equal to 700 degrees Celsius, P1 is equal to 2000 kilopascal, S1 is equal to entropy of steam T equal to T1 and P equal to P1. Similarly, the enthalpy we may need it later on. Okay. At state 2, because the turbine is reversible and adiabatic, we have S2 is equal to S1 and we have been given that the pressure in point 2 is 10 kilopascal. So, H2 is the enthalpy of steam T equal to, rather it should be P equal to P2 and S equal to S2. See, in this particular problem we have made use of the fact that the pressure and the specific entropy are two independent quantities. So, with the help of that we are able to find H2. And so, if I write down, if I take this as a control volume, if I take the turbine as the control volume, so for an ideal turbine there is no heat exchange from the turbine. So, Q dot plus m dot H1 minus m dot H2 minus W dot is equal to 0, this is 0. So, m dot H1 minus H2 is equal to W dot, and W dot, so let me write down, let me divide everything by m dot. So, H1 minus H2 is equal to W dot turbine divided by m dot, which is nothing but the specific work output of the turbine. So, H1 minus H2, we have already found out what H1 and H2 are. H1 minus H2, there we are. Let us run this. So, the specific work is equal to 1397 kilojoule per kg. Okay. Let us find out the heat transfer in the heat exchanger. Okay. Okay, as a matter of fact, we need to find out the mass flux. See, we know what this state is because we know the entropy and the pressure. Similarly, we know what this particular state is because we know the pressure and the quality. What is not known is the mass flux. If the mass flux is not known, I cannot find out the heat transfer from the heat exchanger. So, fine, 1397 is essentially 150 kilowatt by the mass flux, and thus the mass flux is equal to 1397 divided by 150. This is in kg per second. So, then let me write down okay. So, this is what we have, and then the heat transfer from the heat exchanger is essentially the mass flux multiplied by essentially H3 minus H2, where H3 is the enthalpy steam at P equal to P2, x equal to 0. So, the heat transfer from the heat exchanger is minus 250 kilowatt. It is a huge amount of heat transfer, by the way. And so, the heat, as per the sign convention here, the heat transfer to the system is positive, and because we have a negative answer, it means the system or the control volume, this green control volume, is losing heat. Essentially, the heat exchanger is losing heat. It is losing heat to take steam from state 2 to state 1. In fact, just for visualization, let us go ahead and plot all the points. Let me fetch the temperature. the values of P. So, let me do that. Oh, in fact, P is given as 10 kPa. Oh, we know, so P3 is simply P2. So, let me try to go and plot, property plot, steam, what can I draw? So, this is 2 megapascal and we need another plot at 10 kilopascal. On the x axis we have the entropy, and on the y axis we have the enthalpy. Oh, we are missing a value. So, let me just quickly fetch S3. Oops, this is incorrect because this should be x equal to 0. Okay, there we are. We go to plot, overlay plot, H. Okay, so we had something which is lying on this point, okay, something over here, and then it went from this point to this point, and we reached inside the dome. And see, this is the 10 kilopascal isobar, and inside the heat exchanger, because you are losing heat, you go from this particular value of entropy and you decrease, okay, you are losing this much amount of heat. So, essentially the diagram looks like this. So, as a small exercise, I ask you to find out the total entropy generation during the process, and then you have to assume that the ambient is at some 20 degrees Celsius or 25 degrees Celsius depending on where you are, and then see if that checks out with the second law of thermodynamics. It should be always positive, rather non-negative. So, with this we conclude this particular problem. It was a problem in which we had two control volumes. It was a very easy problem, but it highlighted a simple concept that for a reversible adiabatic turbine, the process is also isentropic. So, with this we conclude this session, and I will be back next time with another problem. Thanks.